Shadows.
Hello, everybody. We have, there was a homework due today, and there is no homework due before midterm 2, of course. And so today we will talk on Hooke's law. So, how to say this? There is no homework on what we will cover today, but nevertheless, I will do a lot of examples which should help you to go over whatever we did until now. So it should also act as a review session, but with the feature that there will be a new force that we will be talking about. It's the force associated with a spring. So that, having said that, it's not that it is not important. We will use this a lot in the coming days. It's just a way of introducing it at some time. I was thinking of a homework, but then I thought I should give a small break in the homeworks. That is midterm 2.
Is what we're learning today in the midterm?
No, this will not be in the midterm, but the examples that I will do will be very much part of the midterm, in the sense if I remove the new force that I'm going to talk about today, it's very similar to what we have already talked. So it should be useful.
Quick question.
Yes, please.
Is it okay if I email you my assignment? D2L lagged out on me because I've been having some computer issues. Right as I was trying to send it.
Yeah, do send it to me. And what I've been typically telling to everyone is that if this is a once in a semester, even if it is 2 times in a semester, that's okay. So what I will do is I will not grade the assignment immediately, just to be fair to everyone.
Okay,
but
thank you
if
so
I
much.
realize that it is only once, then I will surely take it into account.
Thank you so much.
Yeah, no problem. So it applies to everyone in general. And there is also a good chance that I will be dropping one of the homeworks by the end. I haven't decided that yet, so don't assume on that. So all these features might get neutralized at the end. So the whole point is that when we have so much grades, a small 1 grade should not affect the total grade. So yeah, but do send it to me by email. That's a simple answer. Midterm 2. This is on Thursday. So that's October 1. Thursday. So it's same as the simple summary is that same as midterm 1. All the ideas we talked about for that applies even here. I will post the midterm. What I did during midterm 1 is that first I sent it by email. Then I uploaded it on D2L and then on the website. So that was the order in which I went, and that was primarily so that I was not sure how much load these websites can take on its own. So I thought emails are the best in that sense. So that was the reasoning I used for that process to go through. But I think all these websites are pretty good and they can handle this much load. We are only about 50 to 60 students, so that should be okay. So use your favorite site and use that. And I usually upload it also 5 minutes before, so that's just for your information. And it will be, time will stop. So time technically stops at 12, what is it? No, 1:50, right? At 1:50 p.m. And with there will be a small bonus time in there, but you pretty much want to count on that. And I don't want to tell you how much extra time I might put in, because then you will think that is the deadline. Last time I had put some extra time. So assume this is your deadline and stick to that. If you're not able to meet the deadline, send it to me by email and I will look into it, what I can do about that. But that will be based on my decision.
So that's the deadline to turn it in, or the deadline to stop working?
To turn it in, D2L will not, I give a buffer time here, but I'm not telling you how much is the buffer time so that you do try to put it in there. You see what I'm saying? Technically 1:50 is the closure time. Last time I had put 10 minutes as a buffer time. So I allowed people to submit until 2 p.m. Does that answer the question?
Yes, thank you.
Mm-hmm. So which means that I understand there is a stress related to that, but let's stick to that. So instead of changing the time, what I did was, or I haven't yet done the paper yet. Last time we had, how much was it? 4 concept questions plus 8 subject questions, right? I mean, if I call it like that, conceptual and subjective questions, what I might do is that I might do 5 concept questions plus 7 subject questions. It's also possible that I might make 4 plus 7. One of those. I'll surely reduce this by 1, but whether to increase this or not, I have not made up my mind yet. So that's what I will do. So there'll be 1 less question. Usually the negative side of that is that you get to lose 1 less point, right? So more the grades, it averages out well. So, but hopefully this will help you with that. Again, the preparation is go by lectures, homework, and textbook examples. And if you want priority in this, I think I would say 1 for homework, 2nd for lectures, and 3rd for textbook examples also. I also sometimes think along the lines of extra credit problems that I have given. Typically, I expect that someone has gone home and thought about it a little. So at least that's what I did last time. The concept questions were sort of based on extra credit problems. So that's something you want to look in. If you want to look into. But typically, if you've done the homework, thought about the homework well, concept questions should be pretty straightforward. Anything else you would like I should go over, or I should mention anything? Anything you can think of? Okay, if not, there's one more point I can say. The next homework will be due all the way October 13th, so, Tuesday. So that's the next homework. There won't be any homework due next week. And midterm 3 is way off October 27th. Okay. I've been using the zoomed in version for the boards, so hopefully that helps too. Okay, so what we want to talk about today is a new kind of force. We remember we talked about the force due to tension, force due to normal force, gravity, and the force of friction. And now we want to introduce another force that is useful. Let me pin the video before I proceed. Okay. View. Okay. This is called Hooke's law broadly. But in the context in which we are talking about, it's good to think of it as a force due to a strike instead of spring force. You're saying force due to a spring. You know, we all know what a spring is, a coil of wire. That's how you want to imagine a spring. So let's have the following scenario. So we have a floor. Let's say this is frictionless. It's frictionless for the moment. This is a wall. And let us say there is a mass kept in here on the floor. Right. And let's have that position labeled x equal to 0. We choose our origin to be where the mass is kept to begin with. Let's tie this to a spring. This is a coiled wire. That's how you want to imagine a spring, as it can stretch. You can stretch this, and you can also compress this. Right? Often we imagine a spring only to be able to stretch it, but we also can compress this. A rubber band is a good example. It doesn't have the form of a coil, but a rubber band is a very good example. But again, that is only stretching itself. The compression part doesn't show up in the rubber band. So in that sense, this coil is a better example. So this is at equilibrium. That means to say that this coil is neither stretched nor compressed. So this will be called the equilibrium position. So that's equilibrium position. Now let's consider the scenario, the same diagram or the same configuration, same system, but I'm going to change this a little by stretching this spring. So this is x equal to 0 again. So that's for reference. That was where the mass was. But now I move this a little to the right. And if I have to do this, I have to stretch this spring. And I'll show that by doing this 1, 2, 3, right? So something like this, right? Extra one, something like that. And it is clear that if you were to stretch a spring, intuitively we expect that the spring likes to be in its original form. So this is going to pull that mass towards this direction. So we will call that F subscript S. And that's what we want to ask, what is that force, or what could that force be? In fact, we'll model that force in a certain form, and that's what we will call to be the Hooke's law. So let's call this extension. So this is state where it is extended. What are the forces acting on this? That is mg acting downwards, and that is normal force acting upward. That's it in those in that first scenario, because the spring is in equilibrium. It doesn't push on the mass. It doesn't stretch on the mass. So if I were to show that explicitly here, let me erase this, but I have some room. And again, show the same diagram here. So this is mg. That's your normal force. That's it. Right, that's only two forces acting here. On this case, in the extended scenario, you have mg acting downwards, the normal force acting upward. The spring is pulling onto the left this time, so that's the force due to spring. These are all vectors, but I've only shown the magnitude in there. And let us say if I don't exert a force now, this will be pulled to the left. So let me keep it in the extended position by exerting an external force. So this is an external force. That means to say that I will have to keep this pulled to the right if I wanted to keep it in this position. Otherwise, it will immediately go to the left. So that's your equations. And let's come back and we'll come back to those equations again. But before that, let's do one more scenario. Again, for reference, that's x equal to 0. This time, let me push on the mass to the left. That's your mass m this time, and this time you compress the spring, right? So this is extended spring, this is a compressed spring, so let me write it here, right? This is compression, extension. Oh, am I in the, yes, I'm still in the extension, and this is equilibrium. Okay, and this time notice when you stretch it away from the equilibrium position, it tries to pull itself to the left. But now, if I were to compress the spring wants to get back to its normal position. So the force the spring exerts is this time to the right. So the idea is that it always points towards the x equal to 0, the equilibrium position. That's where it likes to be. So it always is in the opposite direction of what you're trying to do. Again, if I were to draw the all the forces together, it's called the force diagram if you want. So that's mg again normal force. This time the force is to the right. And if I want to balance it, if I don't
Could you
balance
put the camera down?
it, I'll switch the camera. Forgive me. Thank you. So I was saying, spring tries to exert the force onto the right. If I don't exert another force, that the mass will move to the right because there is a resultant force, right? Vector sum of the forces leads to acceleration, mass times acceleration. So this is not balanced. This will balance this, but this is not balanced. So if you want to balance it, that means if you want to keep it stationary there, then I have to exert another external force. This time it is different from this. That one was to the right. This is to the left. We'll use the same label. Okay, so what exactly is this spring force? How do you model this? Notice that if my stretch was larger, especially if you think of a rubber band, if you stretch it very little, then this force is small. If I stretch a lot, the force is larger. So it seems like the force depends on how much is the stretch. And that's how you will model this. So this is called Hooke's law now. This is, oh, it's too much to the top. This is Hooke's law, and that is mostly to model this spring force. We say that the force due to a spring is proportional to how far the stretch is. It is only a stretch, it is not the x itself. It depends on what the equilibrium position is and the difference from the equilibrium position. So this is your x here, that's x. And in this case, this is your x, which is negative. So the force due to the spring is proportional to x. It depends on x. But then notice that when x is positive, the force is to the left. Right? When the x is negative, the force is to the right. So it seems like you want to switch the sign. So there's a negative sign there. It's negative, and it depends on the x. And it also depends on the material with which the spring is made up of. So there is a material dependent quantity which we will call is as K. So K will be spring constant. And it's good to think of it as a material dependent quantity. And usually you need to get this information from an experiment. You have to perform experiments and actually measure what K is. If you were to plot this, this force as a function of x, so this is the force due to the spring. If you were to plot this as a function of x, that is when x is greater than 0, so that is 0. If x is greater than 0, it's a negative quantity here. And if x was less than 0, it's a positive because less than 0, and then there is a negative sign. So this force, if you were to plot this, it looks like this. And the slope of this line, so K is equal to the slope of this line. Slope, remember, is you get this delta y over delta x. So that's one way of looking at what that spring constant is. What are the units of K? Units of K is, that is, force is measured in newtons, x is measured in length, so newtons per meter. Newton per meter. that's about the force constant. Now that we have a new force in our hand, let's do a lot of the examples that we did in the past in terms of and introduce this new force, and it will act like a review of all those problems also, except that there will be this new feature that will sit everywhere. So let's switch to okay. So one of the earliest example we did was example was just place a mass on the floor, right? But this time we'll make it a small change. I'll place it on a spring, right? So this represents a spring, and one can imagine a small platform there, but it's not necessary. That's your yeah. Actually, before that, I should give some examples for this case. Like, where do you see springs? Like a car, inside a car, if you did not have springs next to your tires, whenever you go on a bump, it could be a very rough feeling. So that is what is called shock absorbers. That's primarily a spring, and so that's a car shock absorber. And one can also think of inside a rubber band, right? A rubber band that many of us use on hair. So that could be another one. So that, let's say rubber band. Yeah, that's another example. Or if you want a spring inside a pen, sometimes if you open a ballpoint pen, inside that you will see a small coil, a metallic coil. So that's also a spring. I will show that after this, while doing this example, we will see that the spring of a car has a much larger spring constant than that of a rubber band or that of a spring inside a ballpoint pen. So that's one thing we can keep in mind. With that example in mind, so let's say this is a car and it's typically it is sitting on 4 springs, but let's imagine that there's only 1 spring in there. And let's ask, what are the forces acting on this? Let me draw the forces here instead of right there because of that spring that shows up with a little clutter there. So mg, that acts downwards on this mass. We have been using that vector sign, but I'm just not writing that. That's only difference. Nothing special. Is there a normal force acting on it? Typically, we would have put a normal force that pushes on it, but a normal force is when it is touching the surface. This time it is not touching the surface, so there is no normal force. Instead, the spring is what pushes it up, right? So the spring keeps it up. So instead of a normal force, this time there is a force due to the spring. Is there a force due to tension? No, no force due to tension, and there is no friction because it is not in touch with the surface, right? That's our equations. Immediately we ask, is it moving? So our Newton's law would be mass times acceleration is equal to force Fs minus mg, right? Earlier we were more, I would have done this in few steps. First write a vector equation and then write this out. We can immediately write this. In fact, we don't even have to write the acceleration. I can say that it's not moving. So we can be quicker. We just say that Fs is equal to mg. If this is not moving, it is static, the forces has to balance each other. So the vector sum of this forces is equal to 0. So if there are only 2 forces, they have to be in the opposite direction. This force has to depend on the stretch here. So this has to stretch a little or compress a little if that has to be at equilibrium. So then we have K times X is equal to mg. Notice that I have taken care of the fact that X, if it was 0, this is in the compressed form, the negative sign goes away. So let me say this is the magnitude of x. So x actually is negative of a negative, so that makes it positive. So let me say magnitude of x. Often we won't write that x at all, magnitude at all, so it will be understood that x is a positive value in that case. So x is equal to mg over k, or k is equal to mg over x. Let's try to evaluate k this time for a moment. So this is mg over x. In other examples, we will actually try to evaluate x. That is, typically k is known for a spring, and we ask how much is the stretch. But this time, just to get a feel for how much k is, let's actually assume that x is given to us. So let's think of a shock absorber in a car, and so a car weighs typically about more than 2,000 kg. So a light car would be 2,000 kg, and the x for this could be about, like, a shock absorber in a car is this about this long. So the stretch in it might be about 10 centimeters, 5 to 10. Let's say 5 centimeters. Right? So that's 5 centimeters, and 5 centimeters is 0.05 meters. Right? We want to be in kg and meters. So how much is k? So k is still, can I? Oh yeah, there's still space. So k is 2,000 kgs times 9.8 and divided by 0.05 meters, right? So this is in kgs, meter per second square, and this is in meters. This is approximately, so let me just do an order of magnitude calculation. I can do this exactly, but we want to have an idea of how big is a spring constant. So just an order of magnitude is good enough. So that's 10 divided by 5. So that's 2. 2 times 2 is 4. And that's 4 into 10 raised to 5. That's really big. And newtons per meter. So if you're talking about a spring in a car, which is very stiff, a metallic spring, typically it's of the order of 10 raised to 5 or 10 raised to 6 even. Like if this is 4, if you increase this, double this, that becomes 10 raised to 6. So that's about 100,000 newtons per meter. So that's a big number, and that is what a car absorber spring constant is. Let's next do the second example, that if you're talking about a rubber band, or let us say we're talking about the ballpoint spring so that we can actually compress it. Rubber band usually only stretches things. Then we are talking about small mass. We can probably talk only in terms of 10 grams. 10 grams is 10 into 10 raised to minus 3 kgs. So this is equal to 0.01 kg. And the displacement, let's say, is about 1 centimeter. So that's another example one can do for this rubber band. You say k is equal to mg over x again, and that's this time 0.01 kgs, and 9.8 remains the same, divided by x. This time is 1 centimeter, which is 0.01 meters, or one significant digit, and that's about 10. That's about 10 Newton per meter. It's 9.8, but let's say that's approximately 10 Newton per meter. So spring, a very weak spring has about 10 Newton per meter. A very strong spring has about 10 raised to 5 or 10 raised to 6 newtons per meter. So you want to keep that in mind when you're working on examples. If you get an answer which is within this range, then it might make sense. So that gives you an example where it is just sitting like this. You can change this immediately. This example to, let's keep this in an elevator, right? We have done examples where things are inside an elevator. And I should also say that a weighing scale, a bathroom weighing scale, actually really works using a spring. That is a small spring inside that scale, and the length, the stretch in that spring is what is used as a sensor to measure the weight. Of course, that stretch might be technologically advanced. It might be a lot more sensitive and a lot more precise in that sense. But in very simple terms, that is all that is happening. So let's do the elevator example. And for that purpose, we can also change this a little bit. I don't have to always compress it when I'm inside an elevator, or even sometimes to, at least in olden days, this was a measurement device used for measuring weights. So when you stretch a spring, maybe you've seen this. So let's say this is inside an elevator, that's a ceiling, and from the ceiling there is a spring that's hanging, and there is a mass hanging inside. Of course, this will be much bigger, but that's a scenario one can imagine. That's your mass M. Of course, this is stretched. This spring is stretched. Only then it can exert a force on that mass M. What are the forces experienced by this mass? Again, we go by the list. That is gravity, since it is close to the surface of Earth. So that's mg. Gravity doesn't have to be really in touch as far as you're close to the Earth, it will experience that force. If you're away from it, it will still experience it. It's just that the expression for it comes out to be g m1 m2 over r square instead of the simple mg as the expression. Is there a normal force? No, because it is not in touch with any of the surface, right? The only thing it is in touch with is the spring. So spring is the only thing that is going to exert force. So no normal force. Is there a tension? One might think this is a rope. No, this is not a rope. This is a spring. So spring is going to exert the force due to the tension instead of the tension. So it is only the force due to the spring that exerts force upward. And now let us say, what is the acceleration of this elevator? Remember, we had 4 classifications. We could either talk about while the elevator is moving upward, it is speeding up. While the elevator is moving upward, it could be slowing down. While the elevator is moving downward, it could be speeding up. While the elevator is moving downward, it could be slowing down. So those are the 4 different scenarios. And if you can also say, while it is at rest or it is at constant velocity. So those were the points we considered before. Overall, we also learned that it doesn't matter what scenario it is only the acceleration that matters. So let's say there is an acceleration upward. So that's your scenario. These are the forces. That's not a force, that's the direction in which it is accelerating. It doesn't mean that it is actually moving upward. Remember that it could be moving downward, but if it was slowing down, that means it is decelerating. Even then, the acceleration is upward. So, so that's your information content in there. And we immediately, like we can write down our vector equation and then decipher this direction. We went through those details, but I can immediately write, oh, mass times acceleration is equal to, has to equal to the difference in the forces. So that's Fs minus mg. I can immediately write that. Earlier, we would have done that in few steps. Let's say, so let me specify the problem. Let me say the mass is, let's say, what should I say, 20 kgs, let's say. Acceleration with which it is going upward is 1.0 meters per second square. The spring constant that's attached to this, let us say, is 10 raised to 2. So I want to put in 2 significant digits. So it's 1.0 into 10 raised to 2 newtons per meter. Right? Remember, 10 raised to 5 is for a strong spring. 10 is weak spring. So this is about 10 raised to 2. So more towards the weaker side of the weak side of a spring. Okay, so, and question is, what is a stretch? Like how much does this stretch? Right? What is x? like how much is the stretch in the spring. That's what we would like to know. This is Newton's law. We immediately see that mass times acceleration has to be equal to the resultant of the forces, two forces acting, spring force and the mg. In this case, this is k times x, where x is stretched in this way, but the force is acting upwards. So this is the magnitude of the stretch. So this time I won't even write the magnitude there. So it is just understood that x is positive in there, and that's minus mg. And that's ma. We are interested in the stretch. So x is equal to, I bring this to the left and divide it out by k. So x is equal to ma, bring it to the left, so that's plus mg divided by k. That gives me the stretch. This is many of you might want to do this in 2 steps. Bring mg to the left first and then divide out by k. I can take mass common out. So if I were to put all the numbers in here, so it's 20 times, I can do 1 and then 9.8, but that's common. So I do 1.0 plus 9.8 divided by k, which is 1.0 into 10 raised to 2. So that's 20 into 10.8 if you want. 9.8 plus 1, that's 10. And then you want to divide it out by 10 raised to 2, which is the same as, how much room do I have? I can go to the next line, I think. This is equal to 216 into 10 raised to minus 2 meters. But it's good to imagine when you're right here, most probably the stretch is small. Meter is probably too big a scale, so work in centimeters maybe. So 10 raised to minus 2 meters is a centimeter. So so that's 216 centimeters, is it? Okay, bad choice. Yeah, bad choice. So what I should have done is, this is a good exercise also, even though my numbers I was putting in my head, I was not taking care of the numbers correctly here. I was going ahead. Now notice that 260 centimeters is a lot. So that's about 2 meters. That's a lot of stretch in there. That means if typically an elevator is of this size and you're stretching it by 200 centimeters, it will go and hit the floor. That means to say that this spring is too weak, right? That was not an intentional, that's my error on my part in foreseeing how much it will be. So we should increase this k. So let me increase this, and that may not change anything. So let's say this, if this was 1.0 into 10 raised to 3, it's probably better, right? If I change that, all this will go through, and down here this will become 1.0 into 10 raised to 3. And then that will change this number to 21.6 centimeters, which is a lot better. It will be within the scale with which we are in. We will be able to measure 20 centimeters is about this much. So that much is okay. So we would, when we are working with 20 kgs, it is better to have a spring scale of about 10 raised to 3 newtons per meter. So hopefully. This is second part of the problem. The first part gives you the box answer. The second box gives you this 21.6 centimeters. That gives you the second example, which we did a lot about 2 weeks back, discussing how the normal force works. The next example we did was on an incline. When something is on an incline, how things move. So again, let's introduce a spring force there, an additional spring force there, and see how things go. So let me move the board. So go back to 1, let's say. And do this. So another example. And this time we have an incline. Right? And let's put a mass in here. And this time, the additional feature is that this incline has a small, tiny mechanism there where you can attach a spring, and that spring is actually connected to this mass. The rest, everything remains the same, and I don't even have to put in the friction. Like I can say there is friction here, or it doesn't matter because I'm going to keep it static, right? This is not going to move. So as far as it doesn't try to move, we don't have friction in there. So the spring force is going to compensate for the gravity. So let's see what are the equations now. What are the forces acting? Gravity acting downward. So that's mg. Let's say this is angle theta. And normal force acts, this is in contact with the surface. The normal force will be perpendicular to the surface. So that's your normal force. And again, earlier we have put all vectors in there, but now we have got used to the system sufficiently. So we just show the magnitude at this point. And if there was a friction here, there would be force of friction also, but there is no tendency to move here, right? The friction acts only when there is a tendency to move, and the spring force is compensating for the force. So there is no tendency to move. So friction force does not act in that, but there is a force due to the spring. So let me show that here. That's the force due to the spring, which will be kx, how much ever this stretches. Right? This is going to stretch this spring a little, and we would like to know what is that stretch. Right? So let's say m is equal to 20 kg again, and let's say k is equal to, this time we learned that it is better to put in 10 raised to 3. So let's say 1.0 into 10 raised to 3 newtons per meter. Remember, 10 raised to 5 is a car shock absorber, very large, strong spring. 10 is weak, so we are intermediate between those two numbers. And we would like to know what is the stretch. How much is the stretch in the spring when there is an incline? And this broadly brings in the idea of what we would do whenever we put a mass on an incline. Whenever something is on an incline, and here there is no tendency to move at this point, but we can imagine if I were to cut the spring off, I can actually, this will slide down, and the acceleration in that scenario gives you a hint of what is a convenient axis. So in these problems, the convenient axis comes out to be inclined, and this is your x, and that's your y. There is an exception when we are doing circular motion. If there is a circular motion, the acceleration is towards the center of the circle. In that case, we again rotate the axis back so that one of the axes is aligned with the acceleration. In this case, we choose our x-axis along the incline. Again, one can write the equations and then write it, but since we have learned those parts now for a moment, so I'll also show the fast way of doing. So if this is angle theta, this is angle theta, and I immediately look at the x direction, and I'm having 3 forces in mind and looking at acceleration. there is no acceleration, right? It's static, so no acceleration. So the x component of this mg, right? Mg is going to slightly pull in this direction, has to compensate for this spring force. So you can immediately say this is mg sine theta is equal to the spring force, which is kx. Or just to clarify how that came about, so what I would have done is that mass times acceleration in the x direction is mg sine theta. Mg is in the fourth quadrant, so its x component will be positive. That's what this is, positive minus the force due to the spring. But the acceleration is 0, so these two have to be the same. So mg sine theta is equal to kx. So it comes from the step. But in diagram, it is much easier to say that, oh, the spring is pulling it in this direction. So often there is a shorter way. Once you get the feel for what's happening, then you can as well write it immediately. In the y direction, similarly, right, the vertical component of mg has to balance normal force because there is no motion again. So mg cosine theta is equal to the normal force. Again, how you would have done here is that there is no acceleration in the y direction. Mg cosine theta is negative because it's in the fourth quadrant here. So that's mg cosine theta. And the normal force is completely along the y direction. That's the normal force. Right? That's how you would have, first you would have written this and then written this form in here. So I just gave you a quicker way of doing it. That's perfectly fine as far as you know what you're doing. This is less error prone. This is more error prone. If you have a lot of experience, this is perfectly fine, especially when there are accelerations going on. It is easy to miss an acceleration in there. We are interested in finding this x, so the normal force doesn't even come up. So just so that I have room, so let me do it here. So this is x. This is this equation here. So x is equal to mg sine theta over k. Right, that's the expression, pretty much the same as earlier. If it was vertical, it is theta, sine theta is 1, but this is having an angle, so the sine theta is something that is added on. Oh, I should have also given you the angle there. So theta, let's say, is 30 degrees. So we have 20 kgs times 9.8 times sine of 30, which is half, and divided by 1.0 into 10 raised to 3. That gives you 20 times 9.8 times half. So it's almost can be done in the head. So it's 98 into 10 raised to minus 3. So it's 98 into 10 raised to minus 3 meters. 10 raised to minus 2 makes it a centimeter. So this is about 9 point, so 10 raised to minus 2 centimeters. That's 9.8 centimeters. I think so. Remember, 1 centimeter is equal to 10 raised to minus 2 meters. When there's 10 raised to minus 1 left, I use that for the decimal. So that's about 9.8 centimeters. That means to say this will be stretched by about about 10 centimeters. So very similar idea. It's just that the context changes, but it gives us a good opportunity to go over some of the examples that we did before. Another example. Next, we introduce the force of tension. And the example. We did an example earlier where there was a sort of a pulley and there was a mass. So this could be, so this is a table if you want. There is a mass M sitting here, M1, and there is a string attached to that, goes over a pulley if you want, and that is an M2G or M2 second mass sitting in there. If this was frictionless, this would have started moving. If there was friction, it depends on whether this is greater than the friction that is that the surface can provide. But let's change the scenario a little bit, since we have a spring now. So let's have a mechanism where this is attached to a spring. So this is a spring now. It's attached to this M1, and that makes sure that this will not move, right? Eventually this will stretch it and this will stay static. At the moment this is static, then there is no tendency to move, and the friction force doesn't matter. So it doesn't matter whether this is frictionless or having friction. Either way, friction will not act on it. Let me clear this up so that I can use this space. And let's ask, what are the forces acting on these masses? M2G here, there is force due to gravity acting on M2, which is M2G. And there is no normal force, not on a surface. There is force of tension though, because there is a rope attached to that. So that's a force of tension. And there is no force of friction, or there is no spring now that we have a new force in there. But the same string is attached to this mass M1. So the idea of a massless spring is that one end, if you exert a force on one end, the force gets experienced on the other end. Right? So the same tension T is exerted on this mass M1. So that's your force of tension. That's getting pulled to the right, which has to be cancelled by the spring will get stretched, and that's your force of spring. So because it is stretched, it will pull it to the left. As far as vertical directions go, there is M1G acting. Oh, this is M2, yeah, M2, M1, yeah. M1G acting downwards, and that is a normal force acting upward. Let's call it M1. Doesn't matter, there is only one normal force. It's okay. So that's your forces. We can immediately say M1 will have two equations. So M1 in the X direction, right? M1 in X direction. So that's one equation. It's static, so no acceleration. We can immediately say these two have to balance each other, right? So it's kind of straightforward. Kx on the left has to equal to the force of tension that is acting to the right. This T has to balance that Fs. We would have written this as a vector equation and identify each one of them earlier, but this is a faster way of doing it. M1 in Y direction, this is equal to normal force, and 1 has to equal to M1G. That's it. Right? No acceleration, so we are just balancing the forces, like almost intuitive in here. And M2 in Y direction, the third equation, which says that T has to equal to M2G. That's it. We are interested in X, let us say. So to specify the problem, let's say M1 is equal to 10 kg, three significant digits here. M2 is equal to 20 kg. And let us say K is equal to 1.0 into 10 raised to 3 newtons per meter. And we could be interested in X. We want to know what X is. And there might be a small confusion as to, oh, do I use M1 here or M2? Which mass decides the stretch in that, and the idea is that it is a force of tension that decides the stretch, but the tension is related to M2. It is not related to M1. So that could be if you're not slightly paying attention, you may not realize that it is the M2 that is coming into picture. And in this algebraically, it is very clear: Kx is equal to T is equal to mg. So Kx is equal to T, which is also equal to M2g. So X is equal to M2g over K, which is a number we used earlier, right? I think so. Probably not. So this is 20 times 9.8 divided by 10 raised to 3. Right, so 9 points, so that's 98 into 2, that's 196, and that's 0.1. Oh, I have to work in centimeters, right? It's better to work in centimeters. So let's write that as 196 into 10 raised to minus 3 meters. I can use 10 raised to minus 2 to convert it into centimeters. 1 goes off, so that's 19.6, but I have only 2 significant digits here, so that's 20. So it is 20 centimeters. And in scientific notation, you would say this is 2.0 into 10 raised to 1 centimeters. Okay, so that's another example. In the last 10 or 15 minutes I have, let me do a slight, very slight, non-trivial. Most of this is repeating the examples that we did. One small feature. So I have to change this 3. Come on. So let's consider another example here, which is having 2 parts to it. And mostly the point is, let's say there is a ceiling here, and you have 2 scenarios. First, you have a spring. This is M1G. And there is another rope you attach in here, and that is M2G or M2. Right? That's two masses hanging like that. And that is case 2. Let me do that here, in which you attach the string first, and then you attach the spring. So that's a string or the rope if you want, and then you have the mass M2. And we would like to know how much is the stretch, like what decides the stretch in the spring. That's what we would like to know. It's all static. Once you leave this, this might oscillate a little, but eventually it will come to a rest, and we are looking at static scenarios. And let's look at the equations. Let's start with M2 here. M2 will get acted upon by gravity. Right? That's M2G. Right. What else is acting on this force? What other forces are acting on this mass M2? There is no contact force. There is no surface in which it is in touch with. But there is a rope that is attached to this, so this will experience a force of tension. So there is a force of tension in here. That's T. There is no friction, so that's the only 2 forces acting on it. When it comes to M1, there is M1G acting downwards. Right? But now this rope is also pulling it down. Right? This M2 actually exerts a force on this M1 through the rope, so it is a force of tension in here. So that's tension P. hopefully that's not too much clutter there. And the spring exerts a force upward, so that's Kx. These two have to balance each other. So T has to equal M2G. These three have to balance each other. So Kx is equal to M1G plus T. But T is equal to M2G. That's M1G plus M2G. Which means to say that X in here, so if you were interested in the stretch here, X is decided by M1 plus M2G over K, which is not surprising. This both masses act together to give the stretch in it. Like after you see through the whole thing, you get very confident that, oh yeah, that's exactly what is happening. Again, these have to balance, but the force of tension is provided by M2G from the second mass. So you substitute this in there, so it becomes M1G plus M2G divided by K. But now what happens in this scenario? Like now one might wonder, how does this work? What decides what is the stretch in the spring here? Again, let's analyze this. That is M2G acting downwards, so that's M2G. This time it's not a force of tension, it is the spring that is exerting a force, so that's Kx. But the spring exerts a force on both the mass M1 and M2, right? Actually, a spring cannot exert a force if you don't keep the other end stretched, right? So it exerts a force on the same force on both sides. So it has to be the same on this side and the other side. So when it comes to M1, it is acting downwards. So that's X. Again, this X should be thought of in terms of the equilibrium position of M1 if you want. But this is the after both M1 and M2 have moved. So what is the equilibrium position of the spring, or the length of the spring, and how much it has stretched. There is also M2G acting downward. That's M2G, or what is it, M1G, so M1G. And there is a force of tension this time acting upward. So slightly different, right? Here the forces that are playing the roles has changed. So what is the equation now? These two have to balance. So T has to equal M1G plus Kx. Right? That's your equation, which is different from what we had in here. And these two have to balance out. So Kx is equal to M2G. So if you ask, what is X being decided about? It's just M2G. You might think that, okay, X appears there also, but force of tension is adjusted in such a way that Kx is M2G. So what is tension T if you ask? So you have to substitute this in there. So that's equal to M1G plus M2G. So force of tension is adjusted in such a way that Kx stays M2G. So what is X in here? X is M2G over K. There might be a small confusion as to, oh, what is that decided by? But after you see this, oh yeah, it is this mass M2 that decides that. But that may not be obvious before you work it out very cleanly, this problem. And with that, I think I can stop. That is all. I'll leave you guys early. Usually I go all the way out there. Unless you have any comments or questions, I can end the lecture at this point. Thank you.
We don't have extra credit.
Oh, I forgot again today, all right? How about this? Estimate question, right? I'll write here. Yeah. Thank you. Okay. Question. Estimate the spring constant of a rubber band. A typical rubber band that you use in your hair. Let us say, often when I was looking into the extra credit work, there is sometimes this complaint that there is not much information given. Whenever I say estimate, the idea is that guess on some numbers. Like think of, guess means guess on some realistic numbers. Think of a rubber band and you ask, okay, if you were to hang some mass M1G on it, how much will be the stretch? Use one significant digit, let's say. It might stretch by about 3 centimeters if you were to hang about 50 grams. So those are the numbers you can use. But I expect you guys to think of it in that sense. That also gives you a feel for how much weight we are talking about, how much masses we typically handle with. One big deal problem here is that we work with pounds typically when it comes to daily life, and in science we use kgs, so that conversion also comes in there. So let's say this is the extra credit question. I should come up with better, I should be prepared with better thought-provoking questions. Yeah, I keep missing out on that. But thanks for reminding. For now, let's make it simple. Thank you.